Hi everyone, this is Mrs. J, and today we're going to learn about the derivatives of trigonometric functions. So I have a quick warm-up for you guys, so please pause the video and give them a try. All right, go ahead and check your work here. So for part A, you could find this derivative using the product rule, but I think in this case it's actually much quicker and easier to actually multiply out this function and then find this derivative just using our power rule. So you should get 3x squared plus 2x plus 2x to the power of negative 2. And then for part B, here we can model the volume of this growing cube with the function just x cubed. So if they ask you to calculate dv dx when x is equal to 3 millimeters, again, we're finding the derivative of volume, and that becomes 3x squared. And then we'll evaluate that when x is equal to 3. And we get 27 millimeters cubed per millimeter. So remember, it's the change in volume in reference to the side length in millimeters. So this just means that when the cube has a length of 3 millimeters, the instantaneous rate of change, that's kind of the key phrase we'd be looking for, the instantaneous rate of change of the volume with respect to that side length is 27 millimeters, again, per millimeter, because it's in reference to the length of the side of the cube. All right, so today in some of the rules that we're going to be learning and proving, there are a couple really important definitions that we need to recall. So these first two limits are limits that we proved in the last chapter using the squeeze theorem, and we said definitely memorize these limits. So this one, the limit as x approaches 0 of sine of x over x is equal to 1. This is just a really important limit to just memorize, but again, we did prove it using the squeeze theorem. And the second one is the limit as x approaches 0 of cosine of x minus 1 all over x is equal to 0. So these two limits we are going to be using to prove some of our rules today. So make sure you have both of these memorized. And then another two things that we will be using today are sum formulas for sine and cosine. So here I put those, the sum and difference formulas for both. So we are going to be using the sum formulas for both today. And remember these symbols here, so mean that if this is a plus, this is a plus, if this is a minus, and this is a minus. If you ever see this upside down plus or minus sign, it means that these are opposite. So if this is a sum, this one will be a difference, and vice versa. So we will be actually using the sum formulas for sine and cosine today in proving a couple of our rules. All right, so before we get to our derivative rules, we're going to try evaluating some limits using those definitions from the previous slide. So this first one, we have the limit as x approaches 0 of sine 5x over 5x. So we can do a little manipulation to use that definition from the previous slide. So let's let theta equal 5x. So if that's the case, we know that as x approaches 0, theta will also approach 0. So we can say the limit as theta approaches 0 of sine theta over theta. And this by definition would just equal 1. So then we could also say that this limit is equal to 1. So essentially any time where this expression inside of sine matches the expression in your denominator, we can evaluate this limit as x approaches 0 to equal 1. So now let's look at this second example. So here we have the sine of 3x over x, and the limit as x approaches 0. So here we need to do a little extra work as well. We would really like the denominator to say 3x. So we can achieve that, but we can't just multiply the denominator by 3. We'll need to multiply the entire thing by 3 over 3. So 3 times the sine of 3x over 3 times x. So again, I just multiplied this function by 3 over 3. And then we could even rewrite this using our limit rules as 3 times the limit as x approaches 0 of the sine of 3x over 3x. And then this limit we can evaluate just like part A. We know that since this and this match, this limit will equal 1. So we just have 3 times 1, which is 3. So you can see that we kind of try to manipulate our function to make it look like those definitions from the previous slide, so then we have something that we can evaluate. All right, let's try a couple more together. So for part A, again, this doesn't look like any of those two definitions from our first slide. So let's see if we can rewrite our function. So we know that cotangent is cosine over sine. So I can do this. So I know that I would like an expression to say sine of x over x. I know that we can evaluate a limit that looks like that. So we can rewrite this function now to look like this. So sine of x over x. So this was in the numerator. So then we can bring it to the denominator of our denominator, and it means the same thing. So again, this might not be super intuitive for you, but remember, we're really kind of going out of our way to create this scenario somehow, because we know that this limit is equal to 1. So now I can actually evaluate this limit. The limit as x approaches 0 of cosine of x is just equal to 1. That's just direct substitution. So this is equal to 1, and this limit by definition is equal to 1. So our overall limit is equal to 1. All right, now let's try this next one. So here, again, let's try rewriting what we see here to involve sine. So hopefully we can create this scenario. So we know tangent is sine over cosine. So our numerator becomes the sine of 5x over the cosine of 5x. And then this denominator, since it's 1 over tangent of 2x, we can rewrite that as the cosine of 2x over the sine of 2x, because 1 over tangent is just cotangent. And then, again, we want to try to create this scenario. So in this portion, I see the sine of 5x. So we really would like to have 5x in our denominator, like right here. But we, of course, need to put it in our numerator. And then here we see a 2x here, so we would like this to say sine of 2x over 2x. So we can get there, we'll start by multiplying this by 2x over 2x, and then we are going to move this down to the bottom. So let me rewrite this now. We have the limit as x approaches 0 of 5x times the sine of 5x over the cosine of 5x times 5x, and I just rewrote it in this order, so these are kind of on top of each other. And then here we have times the cosine of 2x over 2x times the sine of 2x all over 2x. So again, I just moved this down to my denominator here. And again, the reason why I did these is to create these scenarios that we like. So we know that the sine of 5x over 5x, as we evaluate this limit, this will approach 1, or this will equal 1. We know that right here, as we evaluate this limit, this will equal 1. And then we can kind of see what we have left over. So what we have left over is the limit as x approaches 0 of 5x times the cosine of 2x over 2x times the cosine of 5x, which we can simplify just a little bit more. 5 times the cosine of 2x over 2 times the cosine of 5x. I just canceled out the common factor of x. And now we can do direct substitution here. So if we do direct substitution, this approaches 1, this approaches 1, and then all we have left is 5 over 2. Or if you would like to show this extra step, we can pull the constant out and then evaluate this limit, which again is just equal to 1. So this overall limit is equal to 5 over 2. So again, we're really using this definition of the limit as x approaches 0 of sine x over x equal to 1. So we're really going to try to go out of our way to create this scenario when we're evaluating this limits, because again, it's something, it's a definition, it's a value that we know. So some of these steps might seem a little counterintuitive, but the more you do, the easier they get. So now we're going to start getting into our derivatives of our different trig functions. And we're going to start by looking at the derivatives of sine and cosine. So we are going to prove both of these, but the derivative of the sine of x is just cosine of x, and the derivative of a cosine of x is equal to the negative sine of x. So I just want to look at the graphs to see visually why this makes sense. So here's a graph of sine of x. So let's see if we can kind of sketch a graph of what the derivative would look like. So we're going to start with those key points where the slope of our original function would be equal to 0. So that would be at these maxes and mins. So remember, when our slope of our function is 0, our derivative is equal to 0. So we have an x-intercept for our derivative. So our derivative will cross the x-axis at these points here. And then if you look at the slope of our line at different points, let's look at the slope of our line from here to here. It is positive, so it starts out as a very small positive number, then it gets steeper, and then it flattens out again. So in this region, again, our derivative will be positive. It'll look something like this. And then in this region of sine, our slope is negative, so our derivative will be below the x-axis, so it'll look something like this. And you continue that pattern and you see that we actually end up with our cosine graph. And it's the same idea. I know the graph is a little bit sloppy, but I think you get the point. Same idea if you look at the graph of cosine, which is right here. Let's first pinpoint where the slope of this function would equal 0, because that's when our derivative will equal 0. So that's when our derivative will cross the x-axis. And then let's look at the different intervals here. So from here to here, you can see that our slope is negative, so our derivative will be negative or below the x-axis. So something like this. In this interval, our slope is positive or above the x-axis for the derivative. And same thing, now our slope is negative, now our slope is positive. So you can see that as we go through this, we end up with our sine graph, but reflected over the y-axis, so that's why it's the negative sine of x. So next, we're going to actually prove these using our formal limit definition. All right, let's start by proving the derivative of sine. So we are going to use our formal limit process. So the limit as h approaches 0 of sine of x plus h minus the sine of x all over h. So to evaluate this limit, we can start by expanding this expression using our sum formula that I reviewed on that first slide. So the limit as h approaches 0. And remember, for this one, it's sine, cosine, cosine, sine. And if this is a sum, this is a sum. Then we have minus the sine of x all over h. So we still need to do a little bit more work before we do direct substitution here. So let's start by seeing if we can factor. So something you might notice is that this term and this term both share a common factor of the sine of x. So imagine I'm grouping those two together and I'm factoring out the sine of x. So we're left with the cosine of h minus 1 plus the cosine of x times the sine of h all over h. And now if you think of these as two separate fractions, it may help in evaluating this limit. So the sine of x times the cosine of h minus 1 all over h plus the cosine of x sine of h all over h. And now we can do direct substitution to evaluate this limit. So here, if we do a direct substitution for h is equal to 0, well, this is that one of the definitions that we talked about previously. So we know that the limit as h approaches 0 of the cosine of h minus 1 over h is 0. So this would leave us with the sine of x times 0. And then if we look over here, we're left with the cosine of x, this portion, and then we know that this limit is also a definition from our first slide. This will equal 1. So we have the cosine of x times 1, and of course this will just equal 0, and what we have left with is the cosine of x. So we have just proved our derivative rule for sine. And again, you'll see that we needed to use all sorts of things from prior knowledge. We needed to know our sum formula for sine, and we need to know those two limit definitions to help us prove this rule. All right, now let's see if we can do the same process for cosine. It's going to be a very similar process. So the limit as h approaches 0 of cosine of x plus h minus the cosine of x all over h. Again, we are going to expand this using our sum formula. And then for cosine, it's cosine, cosine, sine, sine, and the sign swap. So if this is a sum, this will be a difference. Then we have minus cosine of x all over h. So again, we're going to try to look for things that are factorable. So you'll notice that these two terms share a common factor of cosine of x. So let's group those and factor that out. So leaving us with cosine of h minus 1 minus sine of x sine of h all over h. And again, in evaluating this limit, I'm going to separate it into two fractions just to make it a little more clear. You don't have to show this step, but again, it just kind of helps me when I'm working through it. Okay, so here we can start our direct substitution. So cosine of x will just stay cosine of x. There's no h in that expression. And we know that this, by definition, the limit as h approaches 0 here will equal 0. So again, that's one of our definitions, limits that I said we should memorize. And then we have minus. Well, here the sine of x will just remain sine of x when we do direct substitution. And this, we know by definition that this limit equals 1. So what we have left here, this portion turns to 0, and then we have the negative sine of x, which is exactly what we were trying to prove. So we are done. So you can see a lot of the same kind of methodology here, but slightly different because we need to know the sum formula for cosine. And again, we're just looking out for those limits that we should have memorized from that first slide. All right, now that we know the derivatives of sine and cosine, please pause the video and see if you can find these derivatives. All right, go ahead and check your work here. So just remember that pi is just a constant, just like if it were a 2 or a negative 5. So pi stays pi, and then the derivative of cosine is negative sine. I'm missing one parenthesis here. So our derivative g prime of t is negative pi sine of t. And then here we're going to evaluate the derivatives of each part separately. Remember that this is 1/8 x to the negative 3. Remember to cube the 2 as well. So you can use your power rule for this. So this becomes negative 3/8. So negative 3 over 8x to the 4th. And the derivative of sine is just cosine. So we just say plus cosine of x. All right, so next we're going to see if we can figure out what the derivative of tangent is using our quotient rule, because we know that we can rewrite tangent as sine over cosine. And since we know that these are two differentiable functions and we know those derivatives, we've already proven them, we can now just jump straight to our quotient rule to find this derivative. So we're going to do low d high minus high d low. So the low function is cosine. The derivative of sine is also cosine. So we have cosine times cosine minus high d low. The derivative of cosine is negative sine. And all of that is over low squared. So now we just need to do some simplifying. So cosine squared of x plus sine squared of x over cosine squared of x Hopefully we remember this is one of our Pythagorean identities. Sine squared plus cosine squared is equal to 1. So this is 1 over cosine squared of x, and 1 over cosine squared would just be secant squared. So the derivative of tangent of x is equal to secant squared of x. So this is definitely another trig rule that you will want to have memorized. We're going to do one more proof together. We're going to see if we can figure out what the derivative of secant is, again using the quotient rule, because we know that secant is just 1 over cosine. I do want to remind you that 1 over cosine, this is just kind of a side note, 1 over cosine of x is not equal to the inverse of cosine of x. This is a reciprocal, not an inverse. Let me put a giant X through there. So here, let's just treat this as the quotient of two functions. Our numerator is just a constant function and our denominator is cosine. So let's use our quotient rule again. We're going to do low d high, the derivative of 1 is 0, minus high, and then d low, the derivative of cosine is negative sine, all over low squared. So this just becomes positive sine over cosine squared of x. So we are going to simplify this a little bit. I'm going to rewrite this as sine over cosine times 1 over cosine. And then we know that sine over cosine is tangent and 1 over cosine is secant. So the derivative of secant of x is actually secant of x tangent of x. So again, we were able to find this derivative using another derivative rule that we've already proven and our quotient rule. All right, so here are the derivatives of our 6 trig functions. We did prove 4 of them, and the other 2 you could find using that same process that we did in the last example. But really these 6 derivatives you are just going to want to memorize. So we know the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared. The derivative of cosecant is negative cosecant cotangent. The derivative of secant is secant tangent, and the derivative of cotangent is negative cosecant squared. So, you know, this might seem like a lot to memorize, but there are a few little tricks that we can use. First, for tangent, I like to say, where do you go to get a tan? You go to the sea, like the beach, or the sea. So hopefully that'll remind you that tangent goes with secant, but it is secant squared. Another thing to notice is that both tangent and cotangent have squared derivatives, or derivatives that have a squared function. So if you can remember the tangent, you can really remember cotangent is almost the same. And then also another thing to note is all of the c functions, so cosine, cosecant, and cotangent all have negatives in their derivatives. So hopefully from there you can kind of see some similarities, like between the derivative of cosecant and secant, very similar. The derivative of tangent and cotangent are similar, and same for sine and cosine. So either way, however you get them memorized, these are 6 derivative rules that you absolutely need to have memorized. All right, so now we're going to practice using some of these derivative rules in conjunction, maybe sometimes with the product rule or quotient rule as well. So let's start with finding the derivative of 3 times the secant of x times tangent of x. So here we are going to use the product rule. So we'll consider this to be our first function and this to be our second function. So to find this derivative, we do our first function times the derivative of our second, and the derivative of tangent is secant squared, plus our second function times the derivative of our first. So we have the 3, and then the derivative of secant was secant tangent. So from here, we really just need to start simplifying. So one thing you might notice is that the two terms share a common factor of 3 secant of x. So we can actually factor that out if we would like to. And we're left with secant squared of x plus tangent squared of x. And then just to help us simplify a little more, it's always useful if we can kind of create an expression with all the same trig function. So one of our Pythagorean identities tells us that tangent squared is equal to secant squared minus 1. So if we rewrite that as secant squared minus 1, we can combine like terms a little bit more. So we have 3 secant of x times 2 secant squared x minus 1. And we can leave our final answer like this. All right, let's try this next one together. We could use a product rule for this one, but sometimes when you have a function with multiple trig expressions, it might be nice to check, just see if by rewriting some of these functions, we get something that's a little easier to work with. So if we rewrite cosecant of x as 1 over sine of x, and then we have cosine of x here, we see that we have cosine of x over sine of x, which is cotangent of x. So this is one of our derivatives that we should just have memorized. So much easier than having to do the product rule, although if we did the product rule for this, we would end up with the same answer, just you'd have a few extra steps. So sometimes it works out to rewrite your function. Sometimes it doesn't really help. Like if you look at the last example, if you try to rewrite that, you're not really going to get something that makes it easier. So it is just something to look out for. Sometimes the strategy works, sometimes it doesn't. All right, let's try another one together. Here we're going to need to use our quotient rule. So we'll do y prime. So we have low d high. Remember the derivative of tangent is secant squared minus high d low. Here we'll use our power rule. So the derivative of x squared is 2x all over low squared. So here it's really just a matter of simplifying. So let me just rewrite this as x squared secant squared of x minus 2x tangent of x all over x to the fourth. So you see that there is a common factor of x that we can simplify out. So left with x secant squared of x minus 2 tangent of x all over x cubed. If you want, you could try to rewrite this a little bit more. We know that secant squared is 1 plus tangent squared. Just to make the same trig function throughout. So it would look like this, and then maybe we just distribute the x, and then we kind of rewrite everything in descending order. So we would have x tangent squared of x minus 2 tangent of x plus x all over x cubed. And again, how much you simplify this, I mean, it's really hard to say exactly when to stop or when not to. Would I say that this answer is incorrect? No. But again, just in general, if we can find a way to create a derivative that just has a single trig function, it's usually preferable. All right, we're going to try one more together. So here we have y equals the cosine of x over 1 plus sine of x. So here we'll need to use our quotient rule again. So to find y prime, again, we do low d high, so the derivative of cosine is negative sine, minus high d low. Here the derivative of 1 is 0, and the derivative of sine is cosine, all over low squared, so 1 plus sine of x squared. So now let's just see if there's any way we can simplify this a little bit. If you distribute in this first term, we have negative sine of x minus sine squared of x minus cosine squared of x over 1 plus sine of x squared. Now here, if you really know your Pythagorean identities, you'll see that it might be nice to factor out this negative, and you're left with sine squared plus cosine of squared, which is equal to 1. So again, this is all just equal to 1. And then, so we have negative sine of x minus 1. So then if you factor out the negative there, you have negative and then sine of x plus 1 over 1 plus sine of x squared. And then you'll see we have that common factor of 1 plus sine of x. So you can simplify it just a little bit more, and you get negative 1 over 1 plus sine of x. So you can see how important it is that you really know your trig identities and a lot of your trig formulas as we work through these different derivatives. All right, so to end this video, I have two for you to try on your own. So please pause the video and hit play when you're ready to check. All right, go ahead and check here. So in part A, you're just taking the derivative of cotangent, which is negative cosecant squared, and then cosecant, which is negative cosecant tangent. And then really just rewriting to multiply the negatives. And then for part B, you do need to use the power rule. So the first times the derivative of the second plus the second times the derivative of the first. And here's what you end up with. All right, so that is all for today's video. Thank you so much for watching.